In section 9.6, we'll look at imaginary numbers. We define I as an imaginary number as the following. I squared is equal to -1. So if I take the square root of -1, that's equivalent to taking the square root of I squared. And the square root of I squared, that's I. So now we can say that the square root of -1 is equal to I. For example 1, let's figure out what the square root of -49 is in terms of I. I can rewrite this as the square root of -1 times a 49. Now we know the square root of -1, that can be written as I, so let's rewrite this as the square root of -1 times the square root of 49. The square root of -1 again is I, so this is I times the square root of 49. But I know the square root of 49 is 7, so we could write our answer as 7I. In example 2, we can do the same process. Let's rewrite this as a negative square root of -1 times a 36. We could split this into two radicals. This is the square root of -1 times the square root of 36. The square root of -1, that's I. And so this negative just drops in the front. That's going to give us -I. And we'll multiply that by the square root of 36, which is 6. So this simplifies to -6I. In example 3, we can do the same process. Every single time I take the square root of a negative number, we can just pull out the I to the front, leaving us a square root of 63. Now for 63, we could use the prime factorization for that. 63 can be broken up. 63 is 3 times 21, and 21 is 3 times 7. So we can rewrite this as I times the square root of 3 times 3 times 7. We're looking for groups of 2, so let's circle that, and we'll put the 3 into the front. So this is 3I times the square root of 7. Definition: complex numbers are of the form a plus bi, where a and b are real numbers. For the number a plus bi, we say that a is the real part and bi is the imaginary part. To add or subtract complex numbers, we add the real parts with the real parts and the imaginary parts with the imaginary parts, quite similar to adding like terms. For example, if you have 3x plus 5x, you would just tell me the answer is 8x. Same thing with imaginary numbers. Let's say 3i plus 5i, you would say your answer is 8i. So it's very similar to collecting like terms. For example 4, we'll collect like terms. 23 plus 4, that gives us 27. And then we'll focus on the imaginary component. 3i minus 12i, that all together gives us -9i. And so this is it. This is our solution, 27 minus 9i. In this example, we need to get rid of the parentheses. It's not necessary to have the parentheses in the front here, so we could remove these two. And since this is just an addition, we could also remove this set of parentheses. So now we could collect like radicals or like terms together. I have the 6 and the 7, that together makes 13, and we could add 5i minus 2i, that gives us 3i. So that's it, that's our solution, 13 plus 3i. We cannot add 13 or 3i together. We'll leave it separate. In example 6, we can remove the first set of parentheses. There's no issues with that. So this is equal to 14 minus 6i. For the second one, though, you need to distribute. A lot of students forget to distribute that negative throughout. So this is in fact negative 3 minus a 22i. Again, pretend this is a negative 1 and distribute with that negative. Let's collect like terms. We have 14 and negative 3 together. That's 11. Negative 6i and negative 22i gives us negative 28i. And that's it. We stop right here. Cannot simplify further than that. In example 7, we can remove the first set of parentheses. There's nothing multiplied to the front of it, so we'll just remove it. But for the second set of parentheses, we're going to have to distribute with a negative 1. Don't forget to distribute. Negative 1 times negative 8 is a positive 8. Negative 1 times negative 5i gives me a positive 5i. And then we can finally collect like terms. Negative 2 plus the 8 is a 6, and 9i plus 5i, that gives us 14i altogether. And so that's the simplest we can make this problem. In example 8, we'll just add the imaginary parts with the imaginary parts. Negative 6i plus 20i altogether is 14i. And that's the simplest we can make it. We'll have to stop there. Recall multiplying imaginary numbers that I squared is equal to negative 1. So that's something that you should memorize. I squared is equal to negative 1, and the square root of negative 1 is equal to I. Let's multiply 2i times 3i. That's going to give us 6i squared. But remember, I squared is negative 1. So this is in fact 6 times negative 1, which we can simplify as negative 6. Let's try example 10. In example 10, we will multiply the 12 times the negative 2. That's negative 24. And I times I is going to give us I squared. Again, we have to remember that I squared is negative 1. So this is the same as negative 24 times negative 1, which gives us a positive 24. In example 11, I am going to take the I out of each one separately first before I begin. When there is a square root of a negative, pull out the I to the front. So now we have I times the square root of 24 times I root 45. We can multiply the I times the I together. That's I squared in the front. And we'll have 24 times 45 on the inside of the radical. So what I like to do is I take out the I first, then I can combine the radicals together. We have I squared in the front. That's going to give us a negative 1. And then we could break down 24 and 45 into the prime factorization. So 24 is 2 times 2 times 2 times 3. And 45, that's going to be 3 times 5. And so since we're looking for groups of 2 here, we'll circle the pairs. And that's going to give us a negative 1 times a 2 in the front and times a 3. What's left inside? We have a 2 times 3 times 5 left inside. So this is equivalent to negative 6 square root of 2 times 3 times 5, which gives us 30. So the answer to our problem is negative 6 square root of 30. example 12, we'll do the same process. I'll pull out the I from each one of the radicals because we're taking the square root of a negative. And so I times I, that's I squared in the front, and inside we have 5 times 120. Let's break down 120 using our factor tree. 120 is 12 times 10, 2 times 6, 2 times 3, and 10 is 2 times 5. So we can simplify this as I squared, which is negative 1, times the square root. Let's write down all of our primes. We have a 2, a 2, and another 2. So we have 3 2's, 1 3, and 1 5. That's 120. But we also have that additional 5 from the previous line, so we'll put that 5 for that number. We're looking for groups of 2, so we have a pair here and a pair here. So that gives me a negative 1 times a 2 times a 5 in the front with the square root of, we have a 2 and a 3 left inside. So our final answer is negative 10 root 6. For example 13, we'll use distribution. 3i times 4, that's 12i. 3i times negative 5i is negative 15i squared. Now let's simplify it a bit. We can say that 15i squared is the same as 15 times negative 1. Again, I squared equals negative 1. So we'll do the substitution. And so we write it as 12i plus 15. And typically we want our answer in a plus bi form. So we'll switch this around. We'll write it instead as 15 plus 12i. In example 14, we'll distribute again. Negative 6i times 4 is negative 24i. Negative 6i times negative 5i is a positive 30i squared. And so I squared again is negative 1. We'll replace that with a negative 1. And so this is negative 30 minus 24i. And again, we want our answer in that a plus bi form. And so we just rewrite it in the correct order. For example 15, we are going to have to FOIL. We're going to have to FOIL this problem out. The first with the first, 3 times 8 is 24. 3 times I is a positive 3i. Negative 2i times 8 is negative 16i. Negative 2i times I is going to give us negative 2i squared. So let's simplify this a bit. We have to collect like terms. 3i minus 16i is negative 13i. And again, we have that I squared. So what's I squared? That's negative 1. Negative 1 times negative 2 will give us a positive 2. And so we can collect like terms now. 24 plus 2 is 26 minus 13i. That's our solution for example 15. For example 16, we're going to multiply 3 plus 2i times itself 3 plus 2i. That's what it means when we're squaring an expression. That means we have to FOIL. 3 times 3 is 9. 3 times 2i is 6i. 2i times 3, that's 6i again. 2i times 2i is 4i squared. Let's collect like terms. 6i plus 6i is 12i. And again, remember this I squared is negative 1. Negative 1 times 4 gives us a negative 4. We can simplify. 9 minus 4, that's 5, plus 12i. The conjugate of a plus bi is a minus bi. So it's exactly the same expression except the sign in the middle are opposite in sign. So what do you think the conjugate of 5 plus 6i is? Well, it's got to be 5 minus 6i. Let's recall from last time. If I multiply two conjugates together, we have a plus b times a minus b. This is equal to a squared minus b squared. So we can use this shortcut when filling this expression out. In example 17, they're conjugates. So all I have to do is take the 5 and square it, subtract 6i squared. So this gives us 5 times 5, which is 25. And 6i squared is 36i squared. But recall that negative 1 is the same as I squared. So we can rewrite this as 25 plus 36. Again, negative 1 times negative 36 gives me that positive 36. And so 25 plus 36 is equivalent to 61. In example 18, I have to double check that they're conjugates. Yes, they are. So all I have to do is square the first term, and we'll square the second term. 8 squared is 64, and 3i squared, that's 9i squared. And so the negative 9i squared, since that's a negative 1 there, converts that to a positive 9. So our final solution for 18 here is 73. So when you multiply a imaginary number with its conjugate, you just get a real number. There's no imaginary part to it. To divide complex numbers, we simply multiply the expression so that I is not in the denominator. We don't want the I to be in the denominator. To do this, we multiply the top and bottom of the fraction by the conjugate. We're going to use that conjugate of that denominator. So let's look at example 19. I can multiply the top and bottom by the conjugate of the denominator, which is 3 minus I. Let's distribute. And so 2 times 3 is 6. 2 times negative I, that's negative 2I. Now for the denominator, you don't have to waste your time. You could use the shortcut since these are conjugates. We'll take and multiply 3 times 3, or 3 squared. And we'll also do I times I, or I squared. So this simplifies to negative 6 minus 2I on top. In the denominator we have a 9, because 3 squared is 9. And I squared is negative 1, but we have a negative here, so it actually becomes a plus 1. So this is 6 minus 2I over 10. Now we could reduce this by separating it. We can divide both of these terms by 10. So this is 6 over 10 minus 2 over 10i. Now we could reduce this. I could divide that by 2, get a 3. Divide that by 2, get a 5. So this is 3/5 minus, and I can reduce this again by 2. So this becomes 1 over 5. And don't forget that I. So this is our solution, 3/5 minus 1/5 I, and it's in that nice standard complex form that we want, a plus bi form. In example 20, let's use the conjugate. What's the conjugate of 2 plus 5i? Well, that's 2 minus 5i. So we'll multiply that to the top and bottom of each fraction. For the top, we'll have to FOIL it out. 1 times 2, that's 2. 1 times negative 5i is negative 5i. 6i times 2, that's 12i. 6i times negative 5i is negative 30i squared. And that's just the top. We gotta FOIL out the bottom. But since the bottom are conjugates, we could use the shortcut. So we'll multiply 2 times 2, which gives us 4. And 5i times negative 5i is going to give us negative 25i squared. So let's simplify. I can collect like terms. I have the negative 5i and the 12i together. That gives us a positive 7i. Negative 30i squared, remember this is equivalent to negative 1 times negative 30, so we'll just write a positive 30 on the top. On the bottom, this part right here, negative 25i squared, is actually a positive 25. So on the bottom we have 4 plus 25. Let's simplify the top. We have 32 plus 7i divided by 29. Now this is a good answer, but you could also simplify it in that a plus bi form. Let's rewrite this as 32 over 29 plus 7 over 29i. Sometimes in your homework they want it in this form, a plus bi form. So just take one extra step and write it in the correct form. Example 21. We can do the same process. We'll use the conjugate of the denominator, which is 7 plus 3i. And so we have to FOIL out the numerator. So 7 times 9, that's 63. 9 times 3i is 27i. 2i times 7 is 14i. And 2i times 3i, that's 6i squared. That's just the numerator. For the denominator, we'll have to use the shortcut for the conjugates. We'll multiply the first with the first and the last with the last. 7 times 7, that's 49. And negative 3i times 3i, that's 9i squared. And so let's simplify the top here. We have 63 plus 27i plus 14i, all together that is equivalent to 41i. 6i squared is actually negative 6. In the denominator we have 49. And negative 9i squared is plus 9. So this is 49 plus 9. We'll simplify the numerator. 63 minus 6, that's 57. And we'll bring down that 41i over 58. Now we could simplify this a little bit further. We can say that's 57 over 58 plus 41 over 58i. Just to make it in that a plus bi form. For example 22, again we could use that conjugate trick. We can multiply the top and bottom by negative 3i. You don't have to in this case, but we're just going to stick with the same strategy. Technically you can multiply the top and bottom by I and you would get the same solution. So there's more than one way to do it in this problem. But I'm just going to stick with the same thing we've been doing, and that's using the conjugate. 5 times negative 3i, that's negative 15i. 2i times negative 3i, that's negative 6i squared. In the denominator, we just multiply this out as negative 9i squared. So let's simplify. This is negative 15i plus 6 because of that I squared. which is negative 1 times negative 6. And on the bottom we get 9. So let's simplify this a little bit further. I can say this is negative 15 over 9i plus 6 over 9. And so let's reduce. I can reduce this by 3, I get a 5. Reduce this by 3, I get a 3. So this is negative 5 over 3i plus, and we can reduce each of these by 3, so this is 2/3. Now this is a good answer, but we typically want to rewrite it as 2/3 minus 5/3 I. Again, the real part first, then the imaginary part. So it's equivalent to 2/3 minus 5/3 I. In this next example, we'll see if there's a pattern. I to the 0 power, that's equal to 1. Again, anything raised to the 0 power is equal to 1. I to the first, we know that's just I. I squared, well, that's negative 1. So the first three are by definition or just from our definition. But I cubed, we have to figure out what that is. So I cubed is the same as I squared times I. But we know what I squared is. I squared is negative 1. So I cubed is actually negative I. I to the fourth, I can break that down as I cubed times I. But I know what I cubed is. I cubed is negative I. So this is negative I times I. And wait, negative I times I, that's negative I squared, or negative 1 times negative 1, which gives us a positive 1. So there should be a pattern. If you do I to the fifth, you'll realize that this is going to give us an I. I to the sixth will give you a negative 1. I to the seventh, you will get a negative I. So there is a definite pattern, and you'll see it repeat as 1, I, negative 1, negative I, 1 again, I, negative 1, and then negative I. So there's a definite pattern for powers of I. And each one of these can be broken down. We could say I to the fourth is I squared times I squared, and you'll still get 1. So there's multiple ways to break it down. With the first 4, and then figure out what special powers of I are. But I want you to see the pattern. What is that pattern? If we divide the exponent by 4, now why do we use 4? Well, it repeats 1, 2, 3. Every fourth turn it repeats. That's why we're going to divide by 4. If the remainder of the exponent divided by 4 is 0, then the imaginary number is equal to 1. If the remainder is 1 when you divide the exponent by 4, then the imaginary number is equivalent to I. If the remainder is a 2, then we have the imaginary number is equal to a negative 1. And if the remainder is a 3, then the imaginary number is equal to negative I. So if we have special powers of I, there's only 4 options. And that's all dependent on what the remainder is. So let's try some examples. In example 23, I'm going to take the 23 and we'll divide it by 4. 23 divided by 4 is 5 with a remainder of 3. So what does this 5 tell me? Well, it tells me it's going to cycle to... This 5 tells me there's going to be a cycle where it goes through our sequence of 1, I, negative 1, and negative I 5 times around before it lands on I to the third power. So we can write I to the 23 as equivalent to I to the third power. This 5 just tells me it repeats this cycle 5 times around, and we're going to have our final exponent as I cubed. What's I cubed? Well, I cubed, according to our chart, is negative I. So we only need to remember I to the 0, which is 1, I to the first, which is I squared is negative 1, and I cubed is negative I. If we can remember just these 4, then we'll be able to do each of these exponents with I. Let's look at 30. So for 30, we'll take 30 divided by 4, and that gives us 7, remainder 2. So this means that it's going to go through the cycle 7 times, and it's going to land on I squared. So I to the 30 is equal to I squared. And so I squared we know is negative 1. So I to the 30 simplifies to negative 1. Let's look at this one. This one is 432. We'll just have to divide that by 4. Again, we use 4 because it repeats every 4th turn. And so this gives me 108 with a remainder of 0. And so I to the 432 can be simplified as I to the 0, which we know is 1. So these problems aren't too difficult. You just have to remember to divide by 4 and use whatever your remainder is as your new remainder, and then simplify it from there.